is. Okay. All right. So this is the lecture for April 23rd. We're continuing through logarithms. So there are a couple announcements I'd like to make. Not with a highlighter though. Probably not with a white pen. Okay. Exam 3 and 4 corrections. Exam 3 and exam 4 corrections are still open, so you can still do those if you want to. So remember that that's still an option. So the submission is on Blackboard. Again, yeah, when you go on there, I talk about kind of what I expect from the exam corrections on one of the lecture videos. So if you have any questions over that, refer back to that lecture video or send me an email, and I can help with that. Okay, we have, shake it, STPE, SPT, is it SP? I think it's SPTE. So my evaluations will be sent via email Monday, the 27th. So you have all week to complete them. But it's good, right? So if you can take the evaluations and just let me know how I'm doing, either with the in-class portion or the online portion, any sort of constructive criticism will help. So please fill that in if you can. It'll be sent to you Monday. Finally, we have more information on the final. The final is going to be open from May 8th. Let me make sure that's correct. Where are we at here? May 8th. Yeah, okay, so May 8th at 12 a.m. So midnight, May 8th, first time of May 8th. To May, let me see, it would be 9/11th, right? The 11th is that following Monday. Let me go down here. Yeah, May 11th at 11:59 p.m. Okay, so some stuff about this is that is the time that it's open. So open, okay. You have 3 hours. Try to hold that down. You have 3 hours. Um, so you must complete in one sitting. Okay, so 3 hours must complete in one sitting. Scratch work. Oh, 32 questions. That's how many questions are on it. And it's on Alex. The last thing is just about the scratch work. So the scratch work is optional, but I will give no partial credit without it. Let me write submission on Blackboard. Okay, for review, that's a good question. I'll probably go in and I'll try to get something written up that week. So be looking at, let me see where we at. Okay, so your exam 5 will be be open from May 4th to May 6th will be my plan, or May 4th to May 5th. The first week of that, the first couple days of that week is when exam 5 will be. And then I'll give you some time to prep for this. Really, what you should do is look at your old exams. And, I'll try to make something, but again, I don't make the final, so I don't know what will be on it. So it'll be just kind of, be looking through your previous exams, and then I'll try to put something together or get something that another person used last semester, and try to get that to you. But again, the department makes it, so I'm not quite sure what will be on it. But it's a placement test into college algebra. So I think there are some questions that we haven't covered that they just want to test you over. But yeah, for a review, um, just be looking at like old exams. Um, yeah, I would say the old exams would probably be the best, but I'll try to get something put together for you. Let's see. So exam 5, possibly. Well, hold on. May 7th. Okay, well, let's aim for May 5th. Again at 8 a.m. I don't know why I like this time frame. 8 a.m. to May 6th at 8 p.m. Again, I'm pretty flexible on this time. Does this time work for doesn't work for anybody here? I know it's just you two, but that'll be the tentative date for exam 5. That way you've got one whole day before you even have to think about taking the final. I could move it up a day. I could do like May 4th to May 5th or something like that, but we'll talk about it the closer it gets for exam 5 material. Okay, are there any questions over what we did the last class? Okay, I'll mention that about the review. So just look at previous exams, and I'll try to get something. Wow, something to you May 4th. So I'll try to get it to you that Monday, and that way you've got a kind of a week to look at it. It'll probably be something another professor or instructor has made, um, you know, but that'll be the plan for that. Okay, if there are no more questions, we'll go ahead and get on to the new material. So today we're covering just section 8.4 and 8.5. So we've already talked a little bit about 8.4, but we're into logarithms. So here's a joke for everyone. What do you call a logarithm? So the joke is, what is a logarithm? Wow, I can't spell. Yeah, okay, so what is a logarithm? It's when a lumberjack dances. He has logarithm. So there you go. Guys can laugh at that. Okay, so let's get going. This is just a review saying that the definition of a logarithm is with x and a being positive real numbers.
What about the part where it says, log the y equals log b x is equivalent to by equals x? Is that always true then?
Yeah. So these two are true, right? So if you have this right here, it's the same thing as saying this. So these logarithms and exponents are related. So if I was to give you, log base b of x, that is the same thing as what it would be, b to the y equals x, right? That these two mean the same thing. So a lot of times you'll have to go in between these two forms. And this is, we use this sort of identity to solve from each one of these. So I'm going to go ahead and review going in between each one of these different forms here. So again, this is your logarithmic form. So let's put this in parentheses. This is log form. and you can rewrite it in exponential form. So to do that, remember that you can undo a logarithm, just like if you wanted to take 3x equals 18, right? You can undo multiplication by division on both sides. Here, we can get rid of the logarithm, right? Because we want x, we don't want a logarithm is what we don't want, right? Because we want to go all the way down here to exponential form. So to do that, we match the base here with the base of our exponent. So we use this idea of exponentiation, where we raise this side to b, this side to a b, or we don't raise it. This is our new base, right? So what we're doing is we're actually raising this base to a power of y because we're just lifting everything up, and then here we raise b to this power. And the reason we do that is we match our powers, right? So we have a log base b here and a base of b there, right? Remembering, I don't know if I went through this last time, that um, recall that when you had something like by equals x, that this right here is your base of your exponent. This here is your exponent, right? So you're matching the base here of whatever this exponent is, right, with the base of the logarithm. Okay, so then by doing that, let me rewrite it in a different line here. Let me go. Yeah, so what we do is we end up undoing the logarithm. So this base undoes that base. Let me use a different color. Use green. So now we end up in the exponential form, which is that. Now, the act of doing this is called exponentiation, right? So just like over here, this is called dividing both sides, right? You're multiplying by the reciprocal or dividing by 3. So here, the act of going from here to here is exponentiation. So it's like, it's a different type of operation, but it is an operation, right? That's why we do it to both sides. So let me not do that. Let me go from here to here is I should have learned how to spell this. Exponentiation. That's not how you spell it. Yeah, it's exponentiation. Wow. Okay, yeah, it's exponentiation of b, right? So the act of doing that on both sides undoes it, and you get to here. So now we can go the other way, and because exponents and logarithms are inverses of each other, that's why we're able to go in between these two forms. So if we started in exponent form or exponential form, then now again, you want to match the base here, right? And so like this rule can apply, but we're going the other way. So here you would take the log of both sides. So you have log of b of this side, log base b of that side, right? So we're just like here where we exponentiate on both sides. Here we're taking the log on both sides. And here we're going to have b to the y power. Here we're just going to have x. So we have a nice cancellation here that happens. Let me just copy this down, and then we'll do our canceling that way. If I can line it up with that. Okay, so then here is where the undoing of the exponent happens, right? Like these two undo each other. And so you're left with y equals log base b of x, right? And then this right here is your log form. And move this the chat window. Minimize that real quick. This right here is taking the log on both sides. Okay, so this is just showing that these two mean the same thing, right? That these two are equivalent. There's just I wouldn't even say a trick, right? It's just an identity that lets us go from here to here, right? And we're going to be using this idea more today on how to do those. Is there any questions on going from exponential form to logarithmic form? Again, that was last section, or last lecture is kind of really what we talked about there. So if you do have any questions, refer back to that lecture, and the daily work from Tuesday dealt with that, going between exponential and logarithmic. Okay, so now we can do some evaluating logarithmic expressions. So that means to be able to do this without using a calculator. Depending on what kind of calculator you have, you might be able to do special base logarithms. Most calculators just have log base of 10, right? But so like on a calculator, if you set on the calculator, if you have the log button, this is only for log base 10 of whatever's in the inside, right? So you have to have a special type of calculator. I wouldn't even say special type, but just a scientific calculator that allows you to do a special type of logarithm there for the different base. Okay, so to evaluate these certain type of expressions, notice that, let me get the chat back up here, that what we have here, I'm going to move these over so we've got a little more space to work, is that be aware of the base that we have, right? So we have a base of 8 here with our logarithm. So what we want to know is there any way, right, to take, I'm going to go ahead and put parentheses around here. That way we know that 64 is inside the inside the logarithm. Is there any way that we can take what's inside and make it have an exponent of, or have a base of 8 and then some power, right? Is there a way that I can turn 64 into 8 to some power? Because if we do, then these cancel out because we have a matching base and we're left with whatever the exponent is, right? So, the question is, and hopefully you're thinking, well, yeah, I know what that would be, right? The question is, 64, how can we rewrite that? Well, it'd be with 2, right? Because 64 is 8 times 8, or 8 squared. So that means that we can rewrite the inside of the logarithm here. Instead of 64, we can rewrite it as 8 squared. And so rewriting it that way, we end up with, again, you have a cancellation, right? This base undoes this whole logarithm here, right? So this undoes each other and you're left with just 2. And that is how you go or evaluate this problem here. Now, you could do it a different method if you'd like. You could convert to exponential form and then evaluate it that way, right? So remembering that you have this special relation, which is saying if you had b to the y is equal to x, that is the same thing as saying y is equal to log base b of x, right? They mean the same thing. So another way that you could evaluate this problem is you could say, well, I don't want to have to change this to a matching base, but what you could do is set it equal to x, right? Just put in a variable. And now you can use this identity here, right, to be able to go from one to the other. So it's kind of backwards here because we've got it written differently. So let me write it as this instead. That way it matches with what we have. If we have log base b of x is equal to y, then we know that is the same thing as saying x is equal to b y. Again, that's just the identity there. The ability to go in between these two forms, right? They mean the same thing. So what we can do here is we can rewrite it. right? Again, it's kind of confusing because you've got x, and it may be better to not match what this is, right? You can just do like, I don't know, a, right? And so instead of changing it to a base, to like we did up here, you can rewrite this. So again, you can think of exponentiating, like base here of 5, right? I even like to kind of cheat, don't tell anyone, right, of having a base of 5 here and here, right? That's kind of cutting out some steps, but then these undo each other. So now you have 1 over 125 is equal to 5 to the a power. So the question is, what must a be to make it 1 over 125? Again, now we have this fraction, so it may be better to look at this as 125 to the negative 1, or 1 over 5 cubed, right? Because 5 times 5 times 5 is 125, which is where that comes from. Again, this doesn't look any better, but notice that here we have a fraction, so this is the same thing as 5 to the negative 3 is equal to 5a. So that means that we have a is equal to negative 3. Now, this method I don't like as much, right? The ability of setting something equal, right? Because it's a little confusing that you're using an extra variable that wasn't there. So that's not my preferred method to do these problems, but it's definitely possible to do it that way. Okay, let's try C. Now here, I'm going to use it similar to what we did up above, where instead of using the identity, right, the equivalence of these, I'm going to just try to get a matching base. So here we want a matching base of 1/2. Okay, so let's put this equal to. Okay, so we want a matching base of 1/2, right? So I just rewrote the problem, and we want to use, and I don't know, maybe it'll help having this a different color. So we got 1 over 8. Okay, so what we want is we want a base of 1/2, right? So the question, is there a way, I won't rewrite 1/2 again, or 1/8, right? Is there a way to have 1/2 raised to some power here? Right, the question, can I rewrite 1/8 as 1/2 raised to some power? So the question is, 1/2 raised to something equal to 1/8, right? So be thinking like, what times what times what would give me 1/8, right? With 1/3, well, or with 1/2. Well, hopefully, by looking at this, you see you have 1/2 times 1/2 times 1/2 is equal to 1 over 8, right? So that means this number up here is 3, right? Because we want a matching base of 1/2 here, a base of our exponent. So we have log of 1/2. So we're going to have 1/2 to the 3rd power, right? That's just 1 times 1 times 1. So here is our cancellation, right? This undoes that. And so we just have 3. Okay, any questions over this problem? We've got a couple more examples of this idea here. So you're going to have some practice here looking at it. And your first daily work problem is dealing with this type of problem here. So again, I'm going to solve it like I did both A and B, right, where we just want to match the base, right? We want a base of our exponent to match the base of our logarithm. So I'm not going to do like we did on B. I don't really like the method of B. So I'll use A and C's method here for this. All right, so the first thing is we want the inside of this logarithm to match with a base of 4, right? So our logarithm is log base 4 of 1 over 16, right? So what we want is we want to be able to take 16, 1 over 16, and convert it to a base of 4, again with some exponent here, right? We have to figure out what that exponent is. Well, remember that you have an exponent rule that's saying that if you have 1 over, let's just say a, that is the same thing as a to the negative 1, right? The exponent rule is telling us that is, you know, that is how you can go in between these, right? So you can rewrite your fraction as a base raised to some negative power. And actually, we can go one better. We can say if we have 1 over a to the m, that is actually a to the negative m, right? So be thinking, is there a way that I can rewrite 1 over 16 to be 4 to some power, right? So we don't know what that is, but we want it to be 1 over 16, right? 1/16. So how about instead of 1 over 16, we have 16 to the negative 1 power, right? Now we have a base that isn't a fraction. Or I should say um, we don't have a fraction anymore, right? We have this base here. We have an exponent of negative 1. Well, be thinking that 16 is 4 times 4. So 16 can actually be written as 4 squared, right? And we still have a negative 1 out here, right? I just broke apart 16 as 4 times 4 or 4 squared. So now that you've got matching, or you've got a power raised to a power, you multiply these. So what we find is we've got our missing value here is negative 2, right? We multiply these two together. So what we have is log base. Let me keep with this special base here. 4 to the negative 2 power. So again, and you could have the power on the outside, right? It doesn't affect what's going to happen, right? When it undoes this. We're going to see a rule here later that kind of, deals with this, but these two mean the same thing, right? Your power can be on the outside. So there is your matching base, your logarithmic base matching your exponent base. And what we have is negative 2, right? So that is how you can do those types of problems. Any questions? Okay, moving on. I wanted to do one last example. I think this one looks kind of weird, so I thought it would be good to cover. So again, we just want to evaluate this. But notice we have the fourth root of 3. So here we have another exponent rule that we're going to use. And that exponent rule is saying when you have the nth root of x to the nth power, right, that's going to be x to the n over m. Right, we're going to use this to help us solve this problem here. So actually, let me move this over. We got a little more space to work. Now, this is going to be equal. I'm just going to rewrite this second step here. I'm going to write in with a nice colored mark or colored pin here to know that this is our base, right? We've got a base of 3, and we want to match. We want this to have a base of 3, but I think what we need to do first is rewrite this as a fractional exponent. So when you have nothing written or nothing raised to this power, right, it's just 3, right? So there's actually 3 to the first power here. So using this property, the exponent property here, we have 3 raised to the 1/4 power, right, by applying this power. So now we see again that there is our cancellation, right? We have a logarithmic base matching an exponent base. So these undo each other, and we're left with 1/4. So this reduces down to 1/4 using the exponent rule, as well as them being inverses of each other. Okay, so that is how you do those types of problems. So if you want to evaluate these logarithms, you want a matching base to do that there. Okay, so moving on, we've got graphs of logarithmic functions. So remember that there is what our graph for a logarithm looks like. We've talked about this a little bit last class, so you can check back to that lecture. Now I want to draw a straight line. I don't know how to draw a line on here, so we're just gonna look real quick here. I don't know if I can draw a straight line. Shapes? Oh, I can. Okay, perfect. All right, so let's draw this here. We've got, oh goodness, got a line there. Now, I just want you to again see that these are related to exponents, but moreover, like notice that the graph of y equals log base 2 of x, notice that all of your x values are positive, right? It's getting super negative. The outputs are the closer we get to 0, right? That x is equal to 0 right here, right? So every graph of your logarithm is going to look something like this, and what we're going to find is x cannot be negative, or I should say x cannot be less than 0 um, for y equal log base b of x, right? So you can't have a negative underneath the logarithm, right? So if you had something like y equals log base 2 of, let's go like -2, that this right here is undefined. So this cannot be negative, is what this is saying. Right? We could do a little more exploring here. If you were to write this in exponential form, uh, exponent form, that when you did the conversion, right, you could think of exponentiating, right, by putting a 2 down here. That'll undo the base. Question is, right, 2y is going to be equal to -2. Right? So hopefully you can see like that's why it's undefined, right? Because there's no way, there's no value you can put in here for y that when you raise it to the power, something times itself is going to give you a negative number, right? Like this doesn't work. Right? Because the question is, well, what times, or how many times do you have to multiply 2 to itself to give you a -2? Well, there's no way to do that, right? And we could even think of like a different number. That way there's not so many 2's, right? Think of like negative, let's do one like -4. Right? There's no way to multiply 2 by itself to give you a negative number. So you can't have a negative underneath the square root. So that's an important thing to keep in mind with logarithms. Here's a little extra information that they give you. Uh, it's the domain is 0 to infinity. That means all of the x values are from 0 to infinity that work. Again, this is saying x cannot be less than 0 or x can't be negative. Um, for y equals log base b of x. Right, so that doesn't work. Let's actually use the function notation because it uses that up there in this part here, right? So g of x. Let me try that a little better. And more stuff about this graph. The range is -infinity to infinity. Right, notice that, let me draw it over here. Right, your graph for this function, since we're using orange, let me just make the Cartesian plane in black here. Right, it's going to look something like that. Not perfect, but it's the idea, right? That the range is saying that this arrow is going all the way out here, so you're getting all the positive y values, and you get all the negative y values. That's why we get a range from -infinity to infinity, right? They just go off in different directions. I don't know how you do that on your screen. Okay, your vertical asymptote is 0, which means it'll never cross this line. That is what that's saying. It won't cross the y-axis. That's what that part's saying. Passes through 0 or 1, 0. Again, right, passes through there is what that's saying. Always does that. If b is greater than 1, the function is increasing. If it's between 0 and 1, it's decreasing. So that's what the increasing function looks like. So this is increasing. And this is decreasing. We're not going to have any problems over that, but it could show up in your final. I'm not sure. And it'll definitely show up in college algebra. So it's good just to, to cover it, just to know that you've kind of seen it before you go into that. All right, so that covers the rest of 8.4. We're going to move on to 8.5, Properties of Logarithms. So we're going to look at all the different properties that logarithms have and how we can use them. So the first one is log base b of 1 is equal to 0. Right, again, for the explanation, I can't quite remember what they have here. Right, yeah, the explanation is if you were to put this in exponential form, right? So if you were to go from here to here, if you want to convert to exponential form, we'd have b to the 0 is equal to 1, which we know is always true. So that is why the first one is true. Here, we've been using this property here, right? We've been saying if we've got log base b of 1, right, that notice that the b's undo each other. And the reason is b to the 1 is b, right? So that is what we do here. Again, we've used this property as well. That when we have matching bases, if we have a logarithm base of b, then the exponential base b will just give us p. Again, there's the idea. Then here, our other property that we've used quite a bit is when you raise b to log base b of x, this equals to x, it's because these two are the same and you can convert between those two. So that's just some basic properties of it. But we're gonna go a little bit further here. So notice that you have these relations between exponents. Now, I was trying to think of how to go about this. Let's say we're gonna look at a proof for this very next property that we're gonna have. Let's say m is equal to log base b of a. Yeah, let's go. Trying to think of another letter to use. I don't want to use a. I guess we'll just do x and y. All right, so we've got this, and let's let n equal log base b of y, right? So these two are different. Right, we'll be thinking, like, how can you rewrite this in exponential form? Well, this, again, converting, right? You can think of putting a b here. We might even show this next step, right? You can exponentiate by putting a b. So then your exponent form is going to be b to the m is equal to x. In a similar manner, putting b, you have b to the n is equal to y, right? So these two are the same thing, right? You can go from one form to the other. That's what that's saying. Let me go down just a little bit more. Well, then let's look what happens whenever we multiply x times y, or bm to the bn, right? So the question is, well, what do we get when we take bm times bn? Well, it's going to equal x times y, right? You're multiplying both these sides together. So here you end up with b to the m plus n equals x times y. Again, that's an exponential property, exponent property that we have, right, when you multiply those two. So what happens next? Well, let's convert back to logarithmic form, right? So this is going from log to exponent. So let's take this and go from our exponent to our log, right? So you can think of taking log base b on both sides. So taking log base b of both sides, let me write that down here. So really, what we're doing here is we're defining a property, and I think, I don't know, I think it's a neat way to look at it. What the heck? Where am I at here? We're going to get a property here that we're going to be using quite a bit, right? If I wanted to go from exponential to logarithmic form, that I would take the log on both sides. And again, you want the log to match your base, right? So log base b here and there. So what we have is a nice cancellation here between these. This undoes that. So we're left with m plus n is equal to log base b of x times y. Well, m and m mean this, right? M means log base b of x, and log base b of y is for n, just how we defined it. So what we end up with is our property, right? We end up with log base b of x plus log base b of y equal to the multiplication in the inside. So if you're adding these logarithms with the same base, you actually multiply the insides together, is what that's saying. And that right there is our first property, product property of logarithms. So again, let x and y, or b, x and y, be positive real numbers, because again, remember, you can't have a negative underneath the logarithm. That when you multiply the insides, you're actually adding the outsides, right? So again, it really, to help you remember, be thinking that whenever you have b to the m times b to the n, that you're adding the numerator, or you're adding the exponents here, right? There's a special relation because they're inverses of each other. So you can think when you're multiplying in the inside, you'll be adding these, you'll be able to separate them. So log base b of x times y is log base b of x plus log base b of y. So there's your first property. The next one, I can't quite remember which one is next, so let me move it up just a little bit. Quotient property. Okay, so we can prove it going the same, like in the same proof the one above, but I don't really want to go through all that work. So let's just recall this property, right? Remember that if you have the same base for your exponent and you're dividing these, that what you're going to be doing is subtracting the exponent here, right? So be thinking, if you're multiplying these two, so b to the m times b to the n, you add the exponent. So here, if you take b to the m divided by b to the n and you're subtracting m, what do you think log base b of xy is going to equal? It's going to be really similar up here. And what we're going to find is its subtraction. So again, assuming that the insides here and b itself is positive and not equal to 1, we end up with this right here. So this is our quotient property. Again, it's related, and you could prove it the same way like we did up above by this exponential property. So there is that one there. Our final one is if you had this here, if you had log base b of 2 times 2 times 2, right? This is log base b of 2 plus log base, oh goodness, b of 2 plus log base b of 2, right? That's from up above, right? When you multiply the insides, you can separate them. Well, this is just saying it's 3 times log base b, of 2, right? You've got 3 of these log base 2s that you're adding together, right? And this inside is the same thing as saying log base b of 2 to the third. So what you have here is you have this next property, which is saying the power property of logarithms, right? That if you have log base b of x to the p, that, and again, I had a high school friend who teaches, I should say I have a friend who's teaching high school math that had this, it's right here, had this funny thing that said the exponent jumps over the log, right? It's like a frog jumping over the log. That when you have x to some power, you can move it in front here, and it becomes p times log base b b of x. And really, it's because you're just adding these over and over again, right? By that idea. So what we have here is we have all of the properties. Again, this is really nice. I would have it handy. It's a good list of properties for logarithms. So we're going to use these properties to help expand a certain expression or expression or compress them together. So we're wanting to go being able to use these properties to kind of help us break apart or put together certain expressions. Okay, so here's your second daily work problem. It's finding missing values to make the equations true. Okay, so we've got log base 2 of 11 plus log base 2 of 7. Well, these bases match each other. So remember the property up above says that we can combine these underneath the same logarithm. And when we combine them, we're actually multiplying the insides. So what we have here is 11 times 7, or log base 2 of 77. Move this down just a little bit. I'll move this down a whole lot of it. So this right here is your solution, or 77 is probably what you'd want to fill in. Right, so using those properties, you can put those two together here. Here you've got a missing value here. You've got log base 5 of 7 minus log base 5 of something. Well, when we put them together, we have 7 divided by 3. So again, remember that when you separate them, you're actually subtracting these separate ones. So the missing value here is going to be, oh gosh, what a bad color to use, is going to be 3. Right, 3 is the value that goes in here. And it's because this log base b of x minus log base b of y is going to be log base b of all of them together, and it's actually x divided by y. So there is the property that we use that for. Again, you could highlight this if you wanted to. Oh, I guess you can't. I gotta use my pen. Okay, moving on. Now we're going to use the third property, the power property. We've got log base 5 of 4 is equal to log base 5 of 2 with some number multiplied out in front. So the thing to remember here is, what is log base 5 of 4? Well, log base 5 of 4, let me move it a little bit closer. Again, it's always good to put this in parentheses, right? To know that it's trapped in that value there. So log base 5 of 4 is going to be log base 5 of 2 times 2. Now, at this step here, you can separate it, right? Separate it as log base 5 of 2 plus log base 5 of 2. But really, what you can do is, using the property, this is log base of 5, 2 squared, right? 2 times 2, or 4 is written like that. And so using this other property, this 2, which is right here, is now moved out in front. The property states that we have 2 times log base of 2, and that right there is, oh gosh, that, right? And so 2 would be your missing value here that you would input. Again, the property that we go from here to here is stated up above, that if you had log base b of, oh gosh, x to the p, that it's p times log base b to the x. Again, it doesn't, you can have the exponent in the inside or outside. It gives you the same thing, right? So that is how you do the second type of daily work problem. What we want to do is we want to be able to use those properties to both expand and compress these certain type of expressions. And so now we're in section, this is again 8.5, and its properties. So we're going to be using the properties of logarithms. So again, it would be really good, have those properties, either memorized or handy so you can use them. Properties of logarithms. Okay, so we want to write this following expression. I'm going to move the chat out of the way here. We want to write the, well, hold on, let me just move it like right there. All right, so we're going to write the expression as a sum or difference of logarithms, in regards to x and y, again, assuming they're all positive. So we want to be able to expand this expression using the properties that we have up above. So I'm going to write it over here. So we got log base. Now there's nothing written for the base. So remember that when there's nothing written for your base for your logarithm, you're actually looking at a log base of 10, right? That when nothing is written, it's a log base of 10. So keep that in mind. It'll definitely come in handy here. Okay, so notice here, I'm gonna scribble this out so we're not working by it, right? This is what we're looking at. We want to expand this. Now, we want to expand it using the sum or difference. And to do that, notice we have division. So the division property says that we can separate it with subtraction, right? So we've got a log base 10 here and a log base 10 on the other side, right? And when we separate these, I lost the L, right? This is separated through subtraction, right? And what's in the inside? Well, it's the square root. So what's in the numerator of this fraction? So x plus y. And then over here, it's 10. All right, so continuing on, we can do a little bit more with this square root, right? So there's a couple more things we can do. We got log base. I'm going to stop writing here, but notice this is x plus y. Oh gosh, x plus y to the 1/2 power. Why is it the 1/2 power? Well, remember, it always does this where it doesn't. Huh. That what we're going to use here is the the relation between radicals and fractional exponents, right? So if this is x to the n, then we're going to have x to the n over m. And that is what we used here, right? So we rewrite the square root of x plus 1 as x plus 1 raised to the 1/2 power. Again, this is still in parentheses. Oh, I changed this, didn't I? Right? You can think that that's still in the parentheses, right? That this is where the matching parentheses come from. Let me rewrite it like this, right? That if I see this, sometimes this pen just doesn't work, and I don't know why. Okay, it's a lot of work. I'm just showing that, the parentheses are still there, right? Figure out how to fix that. Okay, so here we move this out in front. Again, another property that we have. Pen is driving me crazy today. I think this is the same. Yeah, it's a little big. Okay, so that is how we do this one. Struggling right now. Get this pen to work. Okay. So we have log base 10 of x plus y. And now we're subtracting. Now here, notice that we have a base of 10 and an exponent of 10, right? What the heck? I don't know. It just like changes the color of that pen. Okay, well, okay, that's just a base of 10, right? So that, oh my gosh, sorry about that. What the heck is wrong with this stupid writing utensil? Okay, so here you get it undone, but notice there's still a base of 10 up here. I'm gonna unplug this stupid thing, plug it back in. Just, nope, good stuff. Okay, but we still have an exponent of 1 up there, so this now becomes minus 1. This right here is your simplified, your expanded form. Notice there's no property to help us whenever we're adding two things on the inside. Okay, continuing on, we've got another example that we're going to be doing something very similar to that. Wow, it would really be nice to be able to use these different. I don't know why it won't work. It needs to go away too. What the heck, man? None of this agitating. Okay. All right. Well, I won't be able to use colors because I don't know why. So log base b of, let's put this in a real big parentheses. So this is the fifth root of x to the fourth yz cubed. All right. So we want to be able to take this and expand it out. Well, how are we going to do that? Well, we're going to use the properties that we have. Okay, so the first property is, notice we have a square or we have a fifth root here, right? So actually, using that property that we had up above, the exponential property, this is the same thing as x to the fourth over yz cubed raised to the 1/5 power. Again, using that same exponential property there, going between radical form and fractional exponent form. Okay, so now what we can do is move this in front, right? Again, that is another property that we had. And so now this is in front of that, this whole logarithm. So we've got x to the fourth yz cubed. Now this one's pretty involved because now notice now we've got division inside the logarithm. So what we have now is we've got this these brackets because we're still multiplying this, but instead this logarithm up here now becomes x to the fourth minus log base b of, oh gosh, y z cubed, right? Again, going from here to here, we separate those. Now here, we can separate it even further because now we have multiplication inside of this. So continuing on, we've got log base b of x to the fourth. We'll deal with these exponents here in a second. All right, so this now becomes log base b, and because we have a -1, right, you can think of this being a -1 out in front of here. We're going to put an extra parenthesis in here because now we've got log base b of y plus log base b of z cubed, right? Because this multiplication in between there. Okay. We've got one last step, and it's to deal with all of the exponents. Yeah, I don't know. I don't know why it does that. All right, because now we're going to be dealing with each of these exponents, right? Because in the other property states that you move the 4 out in front, so you got a 4 there. I'm going to keep with the parentheses. Now here the 3 goes out in front, so now we're positive 3 log base b of z. Now I guess if you wanted to, oh gosh, we need one more parenthesis to match with that one. One more parenthesis there. Now if you wanted to, you could distribute the negative. I don't see why you would, or I think it's good there. But if you wanted to distribute the negative, you could also rewrite this as log base b of x, and now here this is now negative log base b of y minus 3 log base b of z. And that right there is your simplified version, or the one up above as well, but I think Alex would probably want you to do that one. Again, it's using the properties of logarithms to go in between here. Okay, so continuing on, we have a Alex problem. Okay, so this Alex problem is again wanting you to expand this, and it also says don't have any exponents in the final answer here. So I don't know again how to select this because it just being dumb. Yeah, I don't know. I don't know why I can't do it. Basically, it's important to know to not have any exponents here. Delete in the chat window here. Should not have any exponents in your answer. So that means we have to take care of the exponents. So again, it's just like we've done up above. C to the fourth y. Well, this one's not as complicated as the one up above, but again, we can separate this with subtraction. That is our property that lets us do that. And then now we can deal with the exponent, right? The exponent goes out in front here, right? The frog jumps over the log. And this right here is your expanded form. So not as engaging as the one up above, but I would challenge you to try, try working this one out. I mean, if you can get this whole thing, then you're golden because there's a lot of different steps in there. All right, so that is expanding logarithms. The third section is getting into a single expression. So we're going the other direction now. Again, just using the properties of logarithms. Okay, so we're going to rewrite this expression in a single logarithm and simplify. Okay, so let's just rewrite it. So we got log base 2 of 560 minus log base 2 of 7. I'm going to put that in parentheses as well. And we got minus log base 2 of 5. We got a bunch of subtraction, right? And subtraction means we'll have division, right? We can combine this in division. But what I would say is let's first notice that we've got two negatives here. So what if we rewrote this? Oh gosh, 60. What if we wrote this, we factor out a negative, 1, and now both of these become positive. So notice now that we've got multiplication, or we've got addition between these two logarithms, right? So we can combine this in the inside. We got 560. So here, minus, now we're subtracting log base 2 of 7 times 5, right? Well, what is 7 times 5? It's going to be 35. So let's continue on here. So log base 2 of 560 minus log base 2 of 35. Okay, well now we've got subtraction between these two logarithms, right? The base matches, so now we can combine it. So log base 2 of 560 divided by 35. Now I don't actually have my calculator handy, so what is 35 divided by 560? Well, anyone in the chat could help if you'd like to. Am I doing it like that? Yeah, okay. Yeah, it wouldn't be 3. 3 would be too high. 2 would be too high. I think it'd just be 1, wouldn't it? So 35. What do we got here? 1, 0. This drops down to 2, so 21. So how many times does this go in here? Well, 3 would get us close. I mean, 3, 15, and 90. 4, I think 4 is it. Right, because this would be 20. So carry the 2. Again, I'm taking 35 times 4 to 12. Oh, I'd probably go a little bit higher, couldn't I? Because this is 12, so this is now 14. So let's go 5. Again, this is just, I don't have my calculator with me. 5, 2, 15, 17. Again, we can go higher, so let's try 6. Wouldn't be 7. Well, it could be 7. No, let's go 6. So 2, 3, this is 18, so we get 20. Okay, so it's actually 16. Okay, so after all that work, we got log base 2 of 16, right, dividing these two. Okay, well, can we simplify this further? Well, notice we've got a base of 2, so now it's what we had up above, right? In the first daily work problem, are we able to get a matching base with 16, right? The question is, what goes there? Right? Can I rewrite this as a log base of, or with a exponent, or with a base, an exponential base of 2? Goodness, what I'm trying to say. Right? Well, again, you can rewrite 16, right? Well, 2 times 2 is 8, times 2 is 16, or excuse me, 2 times 2 is 4, times 2 is 8, times 2 is 16, right? This is, goodness. This is 4 times 2, right? So this is 8 times 16. So what we have here is 2 to the 4th power. So all of this work simplifies down to 4. So this expression right here, we do all of our work and it simplifies down to 4. So when you're going through here, make sure that, you're using all of the properties that you have. I've got one more example. This example is, before we do our daily work problem, is wanting to combine these. Again, using our properties here. So let's go over here. I like to have this written out with equal signs instead of working straight down, which is why I like to do this. 3 log base of z. Again, an important thing to note is rewrite, simplify the result possible. Okay, I guess they don't want you to, you could have exponents here, but we're just going to combine everything together. That's what we're going to do. Okay, so again, notice that this right here, well, I think what would look better is first add these exponents back, right? So, you're thinking of going backwards here with all of these, right? The frog jumping back over the log. So this is going to be x squared minus log of y to the 1/2 power plus log base z to the 3rd, right? So just rewriting all these as exponents. What are we going to have now? So let's actually look at these first, this first pair here, right? Because what's going to happen here, that's terrible, right? You've got subtraction. So what we're going to have here is everything underneath the same log, but since we're subtracting these, it's going to be x squared, there's a huge parenthesis, y to the 1/2 power. Right, again, remember that y to the 1/2 power is just the square root of y. So I think let's rewrite it like that. Moving down, move this down as well. Right, I'm just going to rewrite it instead of y to the 1/2, just the square root of y. Again, it's a exponential property. Okay, so now notice we're multiplying these, or we're adding the logarithms, right? So we multiply if we combined in the inside. So now this is x squared times z cubed over the square root of y. What goes on between here is notice that x squared divided by the square root of y times z cubed, right? That's over 1. So multiplying the numerator and denominator, we end with this. And there's nothing we can do to simplify this, right? These are just variables. So that is what we get when we combine them. The last daily work example, or the daily work example, the last example for today, is combining this. So again, we're using the same idea that we did up above. Again, combining the single logarithm, I would say first things first, let's deal with our exponents. Right, so we've got a 7 here, right? So 7, hop over the log, 1/4 can hop over the log, 3 can hop over the log. So when we do that, we're going to have log base 2 of y cubed. I like to put those in parentheses. Log base 2 of z to the 1/4 power. Got another fractional exponent. And finally, we've got log base 2 of w to the 7th. Right, so the exponential property is just telling us that we can move that number out in front to the exponent part here. right? So 3 times log base 2 of y is log base 2 of y to the third power. So hops over the log. Okay, what can we do next? Well, again, we've got subtraction here. I think first, let's go ahead and just convert this back to an exponential form, or a radical, right? So this is log base 2. This is now the fourth root of z, log base 2 of, oh gosh, of w, I'll write that a little better, to the 7th, right? So here we are. I just converted this from a fractional exponent to a radical form, so fourth root. Okay, so here we've got subtraction, right? So when you subtract two logarithms with the same base, you can combine them with division. So divide the insides. So this is now the fourth root of z plus log base 2 of w to the 7th. So just like we had in the previous example, the addition means we're going to be multiplying the insides because we have matching base for our logarithms. So our final solution is y cubed times w to the 7th, all divided by the fourth root of z. Again, with this step here being because y cubed divided by the fourth root of z, right, that you're multiplying these fractions, right? You're multiplying the insides here. And that is how you expand and compress these certain expressions using logarithmic rules. Right, we can check our answers. I guess they kept it as a fractional exponent. I don't know. I think having it as a radical looks better. I don't like fractional exponents, but so I wouldn't mark off if you had that. Okay, well that concludes the lecture. It's important to know these logarithmic rules. So I would say make sure you have a copy of your properties here, right? Because these properties are going to help you further down, right? It's going to help you be able to expand or compress these expressions as well as evaluating, with these two. All right, are there any questions? Okay, well, I'm going to stop the recording. Welcome. Again, you'll have some daily work. It's only 4 problems, so be looking at that. Work on some exam corrections if you want. And I will